All right, let's get started. So, good morning, everyone. Welcome to the BRO seminar series. I'm pleased to introduce our today's speaker, Professor Peter Flemings, who is talking about the origins of overpressure at the Macondo well. So, before we start, let me give you a brief introduction about Professor Flemings. Professor Peter Flemings holds the Barrows Centennial Chair with the Jackson School of Geosciences at the University of Texas at Austin. He leads UT Geofluids, a long-running industry-sponsored effort dedicated to developing new concepts and approaches to predict pressure and stress in the subsurface. He served on the U.S. Department of Energy's well integrity team during the Deepwater Horizon blowout, and he was a distinguished lecturer for the American Association of Petroleum Geologists and the International Ocean Drilling Program. His book, entitled A Concise Guide to Geopressure, Origin, Prediction, and Applications, will be published by Cambridge Press in spring 2021. So with that, I would like to welcome Peter to our Friday seminar, and let me turn it over to you to start your talk.
Okay, as was said, my name is Peter Flemings, and I'm pleased to introduce you to a talk on the origins of overpressure at the Macondo well. What I'm going to do here is I'm going to present a very brief discussion of Macondo, and then I'm going to use the pore pressure profile that we observe at Macondo to try to describe three critical processes that control pressure in the subsurface. I'm going to talk about the role of sedimentation. I'm going to talk about how permeable layers result in a redistribution of pressure. And then I'm going to talk about how there can be natural hydraulic fracturing that controls the pressure in the subsurface. And then I'll stop at the very end and briefly talk about some of the implications of these concepts for exploration strategy and natural seeps. Now, I want to start by discussing the Macondo and the Deepwater Horizon blowout. And you all may know it's a decade ago now where the Deepwater Horizon blowout of the Macondo well began in April in Mississippi Canyon Block 252. This was in the news. Tragically, 11 people died, and over the ensuing 4 months, 4 million barrels of oil leaked into the Gulf of Mexico. And this human and environmental catastrophe focused the world on the incredible pressures encountered in the search for hydrocarbons. And again, many of you may remember this was on the nightly news, hour after hour, describing some of the implications of this. This is just one of many slides of the blowout itself when the Deepwater Horizon sank. Again, a summary of the discharge loss on the top, and a truly extraordinary and tragic event. The next slide I show, and it always chokes me up, but 11 people were lost because of this event. And I can't talk about Macondo or even think about my field anymore without really understanding the importance of better understanding the science and engineering of deep water pressure and stress so that this type of event does not happen again. And in many ways, this talk and a lot of our research are dedicated to these people. I had the opportunity or the honor to serve on what was called the Well Integrity Team. And that was a team of technical people that were trying to provide guidance while this blowout was going on into how to cap the well. I actually can't talk about any of the things that I was particularly involved in at this event, but I found this slide online, and I think it's kind of interesting. There are a bunch of people in this room, the CEO of BP, the Chief of the Americas, Stephen Chu, the Secretary of Energy. These people were all meeting day after day in what was called the War Room. And There's this quote here from, at that point, he was the BP director of the Americas. He later became the CEO, where he said it's kind of like NASA and the Apollo 13 mission in there. As for many months, we tried to address the problem of how to cap this well and stop the blowout. In the image on the right, this is a picture of the Macondo well. There's a picture of the stratigraphy shown here with my pointer. There's very complicated casing program. That complicated casing program was driven by the complicated pore pressure profile shown on the right. And as I've already summarized, the Deepwater Horizon was an environmental and human catastrophe. It highlighted the complexity of the deepwater drilling, and there's a well-studied chain of engineering failures that ultimately culminated in the blowout. And I want to emphasize that that's not the job of my talk today. What you're going to see today is a focus on trying to describe and give insight to you about the natural pressure and stress conditions on the subsurface. I do want to emphasize that there are a number of excellent studies. There was a National Academy of Sciences study. There was also an excellent internal BP report. All of these are online if you want to dig into the Deepwater Horizon. And there are 2 papers by Steve Hickman at the USGS and also by Will Pinkston, who was a master's student at the University of Texas and is now working for Hess. And many of the slides that you'll see in our analysis are based on Will's work. And I will re-emphasize that there was extraordinary work by BP describing the pressure and stress conditions. We have worked closely with BP in discussing and understanding and further interpreting those data. Okay, so having said that, my goal now is to talk about this pore pressure profile. And I want to start by giving you a very simple conceptual view of what we mean by when we talk about pore pressure in these rocks. And so in the image on the left, I just want you to consider a small volume element of sediment. The solid grains are shown in gray. The pores are shown in white. And what we want to think about is that this rock has a pore pressure, which I label as U, which is the pressure in the fluid. And the rock itself is subject to stresses. For example, the total vertical stress right here. And something that I'll talk about is what we call the effective stress. The stress the grains themselves feel is the difference between the total stress pushing down and the pore pressure pushing back, because that is what the rocks feel themselves. Now I want to upscale that on the right to what we call a pressure depth plot. And for those of you who haven't thought about plots like this, that pressure depth plot is bounded on the left by the hydrostat. This is the weight of water that you might find as you go down in a swimming pool. And it's bounded on the right by the lithostatic stress. This is the weight of the rock itself. This plot is actually of Macondo. The seafloor is at 5,000 feet, about a mile below the sea surface. And it goes down to about 18,000 feet. And I want you to see that the pore pressure from almost the seafloor itself to a depth of almost 17,000 feet, the pore pressure is very elevated and perhaps almost 80% of the overburden stress. And then you'll see as we approach what's the M56, which is the reservoir horizon itself, there's an abrupt drop in pressure. And again, I'm not going to go into the details of how we characterize that pressure. It's based on numerous direct measurements and also inferences from the state of the compaction of the rock. So in this presentation, I want to ask 3 things about this pore pressure profile, and I want to use it to illuminate what causes these subsurface pressures. First, I'm going to ask, why is that pressure elevated the way it is, down to that depth of 17,000 feet? Second, I'm going to ask, why does that pressure drop? Why is there coupled, what controls the absolute magnitude of that pore pressure regression. And just to comment, this pore pressure regression led to some of the complexities of the engineering decisions during completion of the well. Okay, so the first thing you got to know is that at Macondo, from the seafloor down to the M56 horizon, the sedimentary section itself was extremely shale prone. In other words, there were very few sandstones. It is low permeability. And secondly, it's also immediately in front of the Mississippi Delta. And so that the sedimentation was rapidly occurring during the evolution of this basin. Now, why is that important? We go back to this picture of the rock. And one of the common ways that we think about rocks is what's called a Terzaghi analogy, where we describe the rock as a spring, shown here. And we can imagine if we load that spring, but we don't allow the fluid to escape, the net effect will be that the pore pressure would rise. And my analogy for that would be, for example, stepping on a water balloon. The water inside the balloon is going to feel the pressure of your load. It's one of the most simple concepts in pore pressure. Soft, compressible, and low permeability rocks, when they are loaded, will become elevated in pressure. Then you might ask, well, what is the loading phenomena here? And quite simply, it is the sedimentation itself. So over here on the left, you have a picture. This is the seafloor right here. You can see a fish above that. And what I want you to imagine is that as sedimentation occurs, the seafloor surface is going to rise through time. And there's a long history of studying the broad problem of how sedimentation generates overpressure. And the figure on the right is again a depth on the vertical axis, a pressure on the horizontal axis, and in fact, it's overpressure on the horizontal axis. And the only thing I want you to absorb is that when the pore pressure follows this diagonal 45-degree line to the right, the pore pressure equals the overburden, the weight of the overlying rock. And the bottom line is that this overpressure is controlled by the sedimentation rate in particular, the permeability of the rock, and also how compressible or how squishy that rock is. And at a place like Macondo, we have high permeability, we have high sedimentation rate, low permeability, and highly compressible rocks. Now, many of us don't like dimensionless plots that are somewhat non-intuitive. So what I thought I would do here is just show you a movie example where I've simulated the pressure evolution with a forward model describing the evolution of pressure. So here we go. I'm going to run that movie. Follow your eyes on that red line. With time, the basin is going down. We started in the Miocene, and we're burying that sediment to the present. I'll play that one more time for you. The basin evolves. As the bottom of the basin sinks, we generate a pore pressure profile shown here with the red line, where the red line is, again, about 80% of the way between the blue line and the black line. Not to be discussed here, but the pore pressure prediction heavily relies on this behavior. And you can see that the compaction profile we would expect if there were no overpressure would be the blue line. The compaction profile we see with the presence of overpressure. So my first question was, how do I generate this pore pressure profile shown on the right here? And the answer is rapid deposition of mud-rich sediment can easily generate the observed pore pressure profile of the Macondo well. So next, we want to look at the bottom of this and say, well, what caused this pore pressure drop at the bottom of the well? And this is an expanded view of that pore pressure regression. Pore pressure is almost parallel to the lithostat. Then there's an abrupt drop. And the M56 horizon is the key reservoir interval that was BP's target. To do that, we've got to kind of step back and do a little bit of geological mapping. This is each block here is a 3-mile lease block. The Macondo well is located here with this star. The pink shows the salt stock in green and salt overhangs, sorry, not in green, in dark pink, and salt overhangs in light pink. And what you can see here is that this structure is on the M56, the reservoir horizon. This is where hydrocarbons were trapped at Macondo. And you can see we drop down into a synclinal basin and we come up 18 miles to the south at what's called the Galapagos development, a separate oil field on this structural high. Now, Will Pinkston spent days and months correlating well logs across this basin. If you'll see at the pointer on the base map, you can see the Macondo well at the top. This is one correlation down to that Galapagos development. And you can see tracking this M56 sand across this. So we combined 3D seismic mapping with well log correlation to ultimately build what we would call a hydrologic model for this entire system. And you can see here that cross section. Here's the Macondo well, here's the Macondo structural high, here's that Galapagos development and the structural high at this location. Here's that deep synclinal location in between. And what's striking is that you can measure the pressure at Galapagos and you can measure the pressure at Macondo, the overpressure, and they are identical. And this indicates that this is a hydraulically connected system where a permeable sand can be mapped all of those 18 kilometers across that system. That's actually shown here in this plot on the right. This is a plot of overpressure. That constant overpressure is this green line. That's this color that you also see over in this location. Now, if you add on kind of an approximate model of the shale pressure, that's what's shown in red here. And what you want to imagine is that you have one permeable connected sand body. It's surrounded by these overpressured shales in the yellows and reds. And it turns out this generates an interesting and characteristic pressure profile. And I wanted to give you insight into some experiments we do in the lab to describe that behavior. So in fact, interesting, much of this research is supported by UT Geofluids, and our little image for our consortium is shown in the lower left. And that's because we spend a lot of time talking about this process we call flow focusing. And what I've got here is a little fish tank here. And imagine that white is the M56 sand, a permeable layer. Imagine it's surrounded by much lower permeability material. And I've created an upward flow or overpressure from bottom to top. And what's striking is the large role these permeable layers play in controlling the subsurface flow field. And let me give you an example of that. I'm gonna inject some dyes at each of these ports along the bottom. Remember that we have an overpressured layer at the bottom. There's general flow upward. If we look at what happens to that dye through time, I think you can see clearly that this layer acts as a conduit that sucks in pore fluid at the base. Laterally, that fluid migrates along that permeable horizon and is then expelled at the structural crest. So this is a fish tank, but you want to start thinking about this behavior on the scale of kilometers and tens of kilometers in the subsurface in overpressured systems. Now, there's been a lot of work on this problem. The cartoon on the left is the fish tank experiment we did, and we actually measured the pressures. And I want to draw your attention to pressure highs on the top of this, pressure lows on the bottom of this. There's a lot of historical work doing mathematical solutions to this problem. And here's an example where a permeable layer sucks in fluid at the base, transfers that fluid vertically, and then expels that at the top. Now, what's interesting is when we start thinking about these pressure depth plots, here's pressure, here's depth, here's the hydrostatic pressure, here's the lithostatic stress. What's going to happen is that within this permeable layer in white on the left, the pore pressure always follows the hydrostatic gradient. That line is parallel to that line. And that results in higher pressures at the top of these systems and lower pressures at the bottom of these systems relative to the bounding mud or the bounding shale. So I think the next one's intended just to illustrate a cartoon here for you. Imagine you have this dipping sand body and you're going to drill a well into the foot of that sand body. What's going to happen is as that well goes down, it'll follow the lithostatic gradient, and then all of a sudden there'll be an abrupt fall in pressure. That fall in pressure is because you're penetrating one of these sands in what we would call a down dip location, and so there's a pore pressure reduction. So if we take a deep breath here, my second question was, why is there a reduction in pressure in Macondo? And the answer is that this M56 reservoir is a regionally connected permeable body on geologic timescales, and we are penetrating that well actually in a down dip position. Now that's a little counterintuitive by looking at this, because in fact, the Macondo location A looks to be about the same as the Galapagos location B, but remember, it's the overburden that counts. The weight of the overlying rock here is less here than in this location. And so what does that mean at Macondo? That's location A right here. Your pressure in the reservoir is less than your pressure in the bounding shales, which is this D location right here. And so the pressure regression at Macondo is due to regional flow in this permeable aquifer. So now here's my last question, and it's something that Will and I only came to actually after Will finished his work. Is what's actually controlling the absolute pressure of the Macondo reservoir. And this leads to a discussion of what we call a protected trap system. And I want to just play for you a very simple cartoon. Imagine that you're taking a sand body and you're burying this sand body through time. You could think about this as a turbidite ponded sand that is gradually being covered with shale. And then at some depth, that sand becomes overpressured. Perhaps the sedimentation rate was rapid, or the rock was compacted enough that the permeability was low enough. But now, if I look at the pressure in the middle of that sand, you could see that pore pressure is overpressured. The yellow dot is well to the right of the blue line. And now imagine that this sand body itself rotates. And when it rotates, its pressure at the midpoint will stay the same. But because this is a hydraulically connected permeable body, we can see that at the crest of that sand, we can imagine that the pore pressure will start to converge on the overburden stress. And there are all types of implications of this. You can imagine if the pore pressure is truly at the overburden stress, you're going to start to physically uplift the overlying material. So what's a cartoon of what we think happens? The cartoon is that with this dipping sand and overpressure, that if it has sufficient structural relief, the pressure at the crest of that sand can essentially equal the total stresses in that location. And what we can imagine is if you were at the tip of that sand, the pore pressure here is so high that it will overcome the stresses that are present and it'll drive fluids vertically in a hydraulic fracture. And I think this is really fascinating because this is telling you that there's a natural geologic manner by which you can induce hydraulic fracturing, which is essentially just due to the stratigraphy of the sediment when it's trapped within overpressure. Okay, so let me tell you how we thought about this. When Will originally did his mapping job and was trying to imagine what was controlling the pressure at Macondo, what Will said was, well, the location where the sand is, I think, at its shallowest point relative to the overburden is right here. So in our paper, we have this labeled subsalt leak point. But you need to remember that we couldn't see anything underneath this. We just inferred it would be the obvious location that if you had a leak point, it would occur here. And if you want to think physically about what that means, that's what the cartoon on the right shows. See if I can get this out of the way. What the cartoon on the right shows is, imagine this M56 sand is coming up underneath the salt overhang. And the argument is, at the top of that M56 sand, because it is so structurally high, the pressure is approaching what we would call the fracture gradient, which is itself near the overburden gradient. And at that point, hydrocarbons are just migrating vertically underneath the salt overhang, ultimately to vent at the surface of this system. Now, what was extraordinary to me is just recently in 2020 in the AAPG Bulletin, there is a discussion of this process ongoing at Macondo. And I'll focus you on the slide on the right and tell you that these pink polygons here represent surface oil slicks. These are imaged with synthetic aperture radar. You could go out there today and you can find these seeps on the sea surface. And then the seafloor seeps themselves, they've been investigated by ROVs, and they've been imaged with side scan sonar. And so they've also been physically shown on the seafloor. So it's very clear now that the ultimate pressure at Macondo is controlled by this leak point where the sand is trapped underneath that salt body and it's releasing fluids today. And if you want to think about this practically, the argument is it's like a tea kettle boiling with that flap on top. At this crustal location, natural hydraulic fractures are occurring, which bleeds off the pressure and sets it at the overburden stress itself. Okay, so with that, I tried to address three questions here. The first was, what caused this high pore pressure profile? And what I hope I gave you a sense of is that when you rapidly deposit sediment, the fluid cannot escape, and yet it bears the weight of the overlying load. And it's quite easy, given the actual properties of the rocks we observe in the Gulf of Mexico, to generate this type of pore pressure profile. Then the second conclusion is that this pressure regression is due to the presence of a connected aquifer that occurs over tens of kilometers. And that connected aquifer is controlled by the pressures of the bounding shale and also by the leak point. And what we are doing is penetrating that connected aquifer at a structurally low position, even though we are at Macondo. And then the last point I would make is that the absolute pressure of the Macondo reservoir does appear to be controlled by a leak point, where in a structurally elevated location, the pore pressure is converging on the overburden and the least principal stress in that location, and you're having natural hydraulic fracture driving fluids out of this basin. Now, if I take this to a few broader comments, that I'd really like to just make 3 points. The first is that some fairly simple geomechanical and hydrological concepts, when coupled with an understanding of three-dimensional structure and stratigraphic evolution, can provide enormous insights into subsurface pressures and stresses. And in many ways, in my view, what's happening in the field of pressure and stress prediction is we're starting to really couple the details of one-dimensional pore pressure analysis with the 2- and 3-dimensional view of the subsurface. The second thing I'll tell you is that this concept of flow focusing and protected trap is now a very common tool in deep water exploration, where people will look for a leak point that will establish the pressure in the aquifer system, and then they will look for separate structures. I would add it's also now coming to be recognized even in unconventional basins, where relatively more permeable layers can result in this pressure and stress redistribution in the subsurface. And finally, I think there are probably a few students here, and we spend a whole course in what's called crustal geofluids, combining essentially geomechanics, fluid flow, and geology to understand these phenomena. And to me, the application of that is not only in exploration, it's also in carbon sequestration, and it's also in heat-based energy. So with that, I will stop and take questions. I guess I will stop sharing and see what we do from here.
Thank you very much, Peter, for your interesting time. So I see several questions in the chat box. The first one is from Peter Aquifer. Peter, would you like to unmute your mic and ask your question?
Yeah, good morning, Peter. Very nice and very clear presentation. Also appreciate that you're wearing a tie. I think you're the first speaker in our seminar series who wears a tie. My question is, you didn't mention the presence of hydrocarbons in your pressure prediction. Can you, I mean, I know the basic answer to this, but maybe some of the audience may not appreciate how that would change your pressure profile, and also how in that specific case, actually, the hydrocarbons would have affected the pressure profile.
So, I think what Peter's saying is that all we've worried here are about the water phase pressures of these systems. But in a petroleum reservoir and a petroleum structure, you're going to have a separate oil phase, which is going to be more buoyant and have an extra pressure on top of that water phase pressure. And the answer is there are kind of systematic ways to first study the water phase pressure and then look at how the overprint of the buoyancy of the hydrocarbon pressure is important. But I think what's important is to understand that locally there are hydrocarbons, but everywhere there is a water phase present. And so what we do is we try to reference everything to the water phase pressure, but then where there's the potential for hydrocarbons and the hydrocarbon buoyancy effect to be present, we can include that effect. Now, of course, once the trap is blown, there's no hydrocarbon entrapped, so there's not a significant buoyancy effect. And what you do see in most of these blown traps is that there's essentially no hydrocarbons trapped. They've been vented, and it's your water phase pressure on top of the structure.
All right, so the next question is from Peter Hennings. Peter, you are welcome to unmute yourself and ask your question verbally.
Can you hear me?
Yeah.
Yes,
Peter.
you're okay.
Yeah, it's all the Peters chiming in this morning. Peter, thank you for a great talk. Very straightforward. I'm just struck though, looking at your schematic cross sections, and I realize that the real work is done in very detailed 3D space, but still relies on depth converted seismic data and offset wells and all the rest of that. I'm just struck by the subtleness of the system and your opinion about the degree that we can really do proper hazard characterization pre-drill when we have to tie so many of these things together, understanding whether it's blown or not and how laterally continuous the depositional systems might be that tap into deeper pore pressures. And I've been involved in some of this work myself, but I'm just always struck at the mountain of uncertainties weighing against the consequences of the risk. And if you have any pontification you can provide about our ability now to really do proper risk characterization in these settings.
Yeah. So first of all, one comment would be there's quite a few people on this talk who are I would say related to my field of research from industry, and they spend a lot of their lives talking about and practicing some of these concepts. And I give my really high level answers. Peter, without a doubt, particularly trying to regionally map the plumbing, and whether you have a connected permeable aquifer or whether a fault or stratigraphy has cut that out, is by far the biggest problem in doing this. Having said that, with some offset well data and with higher and higher quality seismic data, you're seeing these techniques being practiced all the time, both for particular well profiles, but also for developing hydrocarbon plays. So I would argue you're right, there's risk. You always got to kind of say, well, if it's connected, it looks like this. If it's not connected, it looks like this. But it's at the point where it's a common tool. But I would say B, companies are spending a lot of money using these concepts in drilling some wells. So it's not easy, but I would say it's now fairly common practice. I'm not sure that answers your question.
Yeah, thank you. It does, and just have to realize that it takes the integration of so many different subdisciplines all working together at the right time with the right amount of data to pull it off, which it's almost always successfully pulled off. And thank you.
You're welcome.
The next question is from Susan Haworka. Susan, you're welcome to ask your question verbally.
Peter, that was a great talk, very clear and educational. Thank you so much. So I'm charmed by the nice documentation of the leak point and how it fits into the geosystem. I assume that the slicks and the leak points were identified post Macondo after people were looking for the impact. So can we make a good case that they're pre Macondo? I mean, it makes sense, but how do you
Sure.
defend it?
No, absolutely. And first of all, the history of this was fascinating. I don't know if anybody remembers sitting around their kitchen table watching TV, but in the middle of this, there was a great hue and cry that there's an oil seep within a few miles of Macondo. Therefore, the well is already an uncontrolled blowout, and it was all across the headline news. By the way, I learned a lot about reporting through this whole experience. What they ultimately could do with the synthetic aperture radar is they could show the presence of these slicks prior to the Macondo well itself. And so the answer is we're sure they were there prior to this. There's also a number of really great examples where you can go out there today and look at the sea surface, see these beautiful oil slicks, all at these crustal locations where the pressure is naturally hydraulic fracture.
You know why we care about finding these leaks, so it's great. Thank you.
Yeah.
All right, the next question is from John Snedden. John, would you like to unmute yourself and ask your question?
Hey, Peter, great talk. In establishing your pressure profiles, obviously you've got MDT data from offset wells like Regal, but for the shale pressures, MDT profiles generally aren't gathering pressure data from shales. So how confident are you in the shale pressure estimations, and in particularly in areas with very few wells?
Yeah, so this is a classic problem in pore pressure prediction, and for those, the bottom line is that in the shales themselves, the dominant tool is to look at the degree of compaction of that shale and relate how much compaction there is to the effective stress, and then to back out the pore pressure. And this technique, boy, it started in the 50s with Hubbard and Dickinson and others, and then we are still trying to figure out better ways to do it today. The bottom line is there are a lot of techniques. A key part of those techniques, John, is you try to look for pore pressure measurements. When you're trying to calibrate this technique, you look for pore pressure measurements with the MDT in the permeable layers, but you look for them in sands that are small and don't have much regional extent or structure. So it's not affected by this flow focusing effect that I've been talking about. So we are always left, particularly in new basins where we don't have a lot of direct pressure measurements, with approximations of the pressure profile. And it's a continuing field of study to come up with better techniques to relate the degree of compaction to the pore pressure profile itself. And we could talk a lot more about that. But I think that's the short answer.
Thank you.
All right, so I do not see any further question in the chat box. So is there any other question for Peter? You're welcome to unmute your mic. Okay.
I'd like to ask a question. This is Mark Cluse. Peter, very interesting. Nice to hear you give a presentation. I got a couple questions though. One of them is you gave us a non-dimensionless plot and all, but you actually must have real data here in terms of what truly are the sedimentation rates going on in this area to lead to these spectacular fluid pressure. And then the other one is the issue of this I guess it was M56 or whatever the name of your sand horizon was that was traced around. It obviously has great lateral continuity. What is the nature of that horizon from a depositional perspective to be so continuous that it can act as a 10-kilometer plus scale aquifer?
Let's see. Let me take the second one first, Mark. You sound like many people I've had discussions with about these lateral connectivity issues, and the answer is that's a submarine turbidite amalgamated channel facies. It has a lateral extent on the order of a mile, but not 10 miles. What I mean by lateral, I mean cross section, like the width of a river. And it itself is made up of individual sand bodies that are all interacting at some locations, but it's not one connected permeable body. One of the things that came up during the actual blowout is that when we first modeled it as one perfectly connected permeable body over production timescales, the pressure decline observed from the blowout was too large. And so that's what led to a more complicated stratigraphic model where there's some connectivity over geologic timescales But if you actually pull that with, for example, a production like the blowout, you'll have significant drawdown. That turbidite channel system was essentially an exploration target for BP on a number of structural highs. And so they mapped that regionally as part of their exploration strategy. So that's, and Mark, I've had a lot of conversations where people say there's no way you can connect that sand 18 miles, or a lot of people do it a whole lot further. And the answer is, I think there's absolute evidence in the Gulf of Mexico that there are some permeable bodies that can be mapped over many, many miles that record this behavior. The second comment is, you're right, I didn't go into the detail. That's a Miocene deposit. A lot of the deposition rate was between 0.5 and 1 millimeter a year. And what we've done in our group is we've actually measured the permeability and the compressibility of these shales. And what you saw was a simulation of those characteristic properties and characteristic sedimentation from Macondo that generated those overpressures. I think what people often forget is in these shales, the enormous amount of compaction that has to occur to get, and that means you got to drive off a lot of fluid. And so it's the combination of how compressible the rock is with how permeable that mud rock is that generates those overpressures.
Hey, Peter, this is Scott Tinker. Can you hear me?
Yeah.
Great. Really appreciate the talk and all these good questions. I just wanted to share a little bit from a slightly different angle on this. I was on what BP called their Technical Advisory Council at the time. It's 7 or 8 external members and upstream and downstream when Macondo happened. And we saw a lot of data, not all of it for sure, but I just wanted to mention, I think your talk helps highlight this, the combination of both technical and then human decisions that go into something like this, and the accident disaster that happened are real, but the resources that were deployed and the learning that was going on in real time was absolutely phenomenal from an inside the company perspective. And David Rainey on our own advisory council was quite involved with that, as were others. And for the younger people that are on this, sometimes the industry is painted as negligent or incompetent and other. I just couldn't believe what we were learning in real time and the different strategies being deployed to shut down that well, and what was done from zero to actually at the end drilling a new well without a pro forma all the way down and intersecting. It was phenomenal to me. And I wonder, do you have any thoughts and comments on that, just from a perspective of the industry response and what's happened since then to make sure, or try to make sure, that something like this doesn't happen again?
So I'll make a couple broader comments. The danger of trying to give a talk on something like Macondo is that there are a lot of people who really gave a significant fraction of their life to solving this problem, and who also lost good colleagues, and who also really felt they had to defend their company. I will say the one thing I was impressed with in every step of the way when I was at BP was the technical excellence, both of the BP people, but also the partners. There were problems. The problems there were definitely related to the completion of that well and not the original pressure description. So there is nobody in industry who is that I ran into who are making shortcuts or who are not facing these problems. But the flip side of this, which is what I've tried to emphasize, is these are enormous pressures. These are complicated wells to drill. I think we've gotten much better at this, and we're going to keep getting better at this. And it begins with really a technical study. I'm not sure I said that very eloquently, Scott, but I do want everybody to understand that I came away from this experience not with a feeling that the industry was abusing its right to be out there, but that enormous effort is put into doing this right. That you could give a separate talk about. I'll never forget being in Houston, and at one time they probably had 30 vessels out there. They were shooting seismic. They were drilling a separate well. We went through all of those 4 months without a single accident occurring. Maybe I'll leave it at that, Scott.
No, thanks. I appreciate your perspectives there.
Okay, Gillian just made a comment. Thank you, Scott, for recognizing the work BP did. And the next question is from Jamie Hernandez. Jamie, you're welcome to ask your question through your mic.
Thank you. Yes, my question is if the sand, the reservoir is, as I understood, is a deep, probably a deep turbidite. It comes from, what could be the source for that sand? And also the other question is if we have, you said that we have the possible, that sand is connected with the site that is next to it. Is possible to have that sand like at the same regime but separated or not?
So the data are as good as they are, and the reality is for us, we could make a structure map off a reflector. We can infer similar sand body log character at the appropriate depth, but there's no way we know per se if it's exactly connected as we propose. But you are left with the striking observation that those pore pressures are within about 30 psi across 18 kilometers. And so it's an inference drawn from the data you have, but other interpretations are certainly possible. And in a way, I think that's what Peter Hennings was commenting on, and also Mark Kloos. As for the sand source of the M56, I hope John Snedden might still be on the phone for me, or somebody else, maybe with BP, who is part of that team. I can't give you a detailed answer to that.
Yeah, if I could comment, these sands that are present are part of the main, let us say, sand lobe system that makes up the really the middle and upper Miocene Macavelu fan system that we have mapped all over the basin, all over this part of the basin. Certainly a large scale system from Thunder Horse all the way to Galapagos and other places. And I can also make a comment about BP. They just finished drilling a very deep, expensive well at Galapagos called Galapagos Deep, safely and without any incidents. So, I mean, clearly industry can drill these type of wells safely. Thank you.
Okay, and I believe Julia Gale has a question. Julia.
Hi, Peter. Thanks very much for the presentation. I enjoyed it a lot. So I have a little question and then a follow-up about the overall pressure profile. And early on in the talk, you put up a representation of the sediments in the pile, and you made the comment that it was a very shale-dominated system. But I was looking at it, and there were a few little yellow things. And when I looked at the overall pressure profile, there are some smaller excursions towards the hydrostat further up in the column. And I just wondered if any of those had been tied to other sands. And then the follow on from that is there a way of kind of figuring out for a given system, and it would vary with depth, what scale of sand would you need and what amount of lateral connectivity would you need In other words, could you predict ahead of time which sands might be the problem or a problem?
So let's answer the first question. Without a doubt, in a way that image I showed you did show some yellow, but I would tell you that's the cuttings. And basically, if you look at the cuttings, it never really gets above about 30%. But your point is valid that there are certain permeable layers in that shallow section where pressure could be measured. And in fact, in many cases, the pressure we interpreted in those locations was not measured in the well. It was measured in an offset location called Regal that we extrapolated to that location. So there were what we would suggest would be smaller localized sand bodies that could be used to estimate the pressure in the Macondo well. So there are sands, they're small, they don't have significant structural relief, and we did use them to calibrate the well pressure. I think maybe your broader question is when in terms of being able to understand whether these permeable sands affect the overall pressure distribution you might expect in a well, when does it become important? And the first answer is that any permeable sand will show this behavior, but the degree to which the process becomes important is to the degree to which there's significant structural relief. So the thing that you look for are what you interpret to be a connected sand body, but in particular with significant structural relief. And so that's what, and then we have various quantitative techniques actually, where given the geometry of the sand and our estimate of the pressure in the surrounding shales, what the pressure will be in that sand at that location. Did I answer your question?
Yeah, that's pretty much what I was looking for. Thanks.
Yeah.
All right. Thank you, Peter, for addressing the audience questions. So we need to conclude the session at this point. Thank you very much. Thank you again for your time and for your interesting talk. And thank you everyone for attending and for your great questions. Hope to see you next week. Have a wonderful weekend.
And thank you for all the external people that joined this meeting. I appreciate it.
Thank you. Have a good one.
Thank you, Peter.